Hey everyone, my name is David Brown and welcome to this video series about abstract algebra. In this series I'm going to work my way through this book, which is Abstract Algebra, a First Course, 2nd edition by Dan Saracino. This was the textbook I used when I took abstract algebra in college. And I do have a bachelor's degree in math, but I'm not a math teacher. What I'm trying to do is work back through some of the math that I learned in college and also try to extend my knowledge of math. So the main plan in this course will be to work my way through this book section by section and take notes and then explain those notes through these videos. I know there's a lot of math YouTube channels that are really good about being high energy and putting graphics on the screen and things like that. For this series I won't do that. It'll be more low-key, just talking and me explaining my notes, and so it'll help me understand what I'm learning, and I hope that some other people might find it useful as well as something to listen to while they're doing other things or while they're trying to fall asleep, something like that. So we'll just work our way through this book together and do our best to try to understand it. And the focus on my notes will be more on things like definitions and theorems rather than proving anything. I know when you take this as an actual course in school, especially the professor I had, we went, I would say, at a very slow pace with a strong emphasis on doing proofs. That's not the point of this series. This will be more to go through the sections, see what are the results, what are the new definitions, what are the theorems, and if you want to do the proofs, you can of course do that, but the focus will be more on getting through the material so that we can get a basic understanding of what abstract algebra is all about, and then if you want to do proofs later, you can build on that foundation. So today we're going to deal with section 0, which doesn't really get into abstract algebra. It's more of a review of sets. And by the time you take this, by the time you take an abstract algebra course, you've probably already been introduced to things like sets. In my college, we had a class, I think it was called Foundations of Math, that went through the basics of proof writing and a lot of the basic concepts from the higher level math courses like abstract algebra and real analysis. So this section will go over proofs a bit and also mathematical induction. So the first definition it gives is set, and it defines set as a collection of entities which are called elements or members of the set. And then it goes through the notation of what it means for X to be a member of the set S. And we can define a set by explicitly listing the items. We can say that S is a set that contains, for example, 1, 2, 3, and 4. We could also express that such that S is the set of all X, where X is a member, where X is a positive integer less than or equal to 4. So when we're defining sets, there's multiple ways to do it. Sets can also be infinite, which we could express, such as S is the set that contains 1, 4, 7, 10, 13, 16, and so on, which could also be expressed that S is the set of X such that X is of the form 1 plus 3k, where k is a positive integer, something like that. Then it goes through and it tells us the notation of some common sets. So these are expressed as letters, which are usually a little fancy. So the first one is the set of all integers is represented by a z, but the z has like 2 lines instead of 1. Q is the set of all rational numbers. R is the set of all real numbers. C is the set of all complex numbers. And then we have the empty set or the null set, which is the set with no elements and is represented by an O with a line through it. Next, we move on to the definition of a subset. And we have if S and T are sets, then we say S is a subset of T, and it gives the notation, if every element of S is an element of T. So one set is a subset of another set if all of the elements of the first set are also in the second set. So visually, this makes sense, right? we think of a subset as being a smaller part of something bigger. So anything that's a part of that smaller set would have to be part of the bigger set. Now, because of the definition of subset, for any set S, S is a subset of itself because it holds, the definition holds. And likewise, the empty set or null set is also a subset of every set. So just build into the definition, just be aware of that. Every set is a subset of itself, and the null set is a subset of all sets. Then we have the definition of two sets being equal. We say two sets, S and T, are equal, denoted with an equal sign, if S and T have the same elements, which is the same thing as saying that S is a subset of T and T is a subset of S. Okay, if those things are true, then the two sets are equal because they're basically the same thing. They contain the exact same elements. Next, we get the definition of a proper subset. If S is a subset of T, but S is not equal to T, then we say S is a proper subset of T. So basically a proper subset is just a subset that isn't the same set, because we said that every set is a subset of itself. So if that's the case, then that's the only case that's not a proper subset. All the other subsets are proper subsets. If we're just saying the set is a subset of itself, that's not a proper subset. Next, we have the definition of intersection and union. Again, concepts that you've probably already been introduced to by the time you get to this course. So the intersection of two sets, S and T, is defined as all X, where X is a member of S and X is a member of T. So the intersection is just this, all of the elements that are a member of both sets. You can think of it almost like a Venn diagram, right? You have two circles. The intersection would be the part where they overlap. S union T is the set of all X such that X is a member of S, or X is a member of T, or both. So for intersection, each element had to be a member of both. For union, we're saying it just has to be a member of one of the two, or it can be a member of both. So if we're thinking in terms of two circles that make up a Venn diagram, we said the intersection was the area where they intersect, right? Where they overlap. The union would just be the total of both circles, including the part where they overlap, but also the parts that are just one of the two and not both. So pretty simple concepts. Okay, now we get to theorems. Theorem 0.1, let S and T be sets, then S is a subset of T if and only if S intersection T equals S. So what does this mean? First of all, it's if and only if. And when we prove these statements, we have to prove it both ways. So we assume the first and prove the second, and then we assume the second and prove the first. Now, when we're dealing with subsets and intersection, both concepts have to do with what elements are members of sets, right? So when we say S is a subset of T, we're saying that any element that's in S is also in T. When we're saying the intersection, S intersection with T is equal to S, what does that actually mean? Well, intersection are the elements that are in both sets. So if the elements that are in both sets are exactly equal to the elements that are in the first set, S, that means that all of S is contained in T, because if there was an element of S that was outside that intersection, then the intersection would not equal S. So next, we move on to another definition, the well-ordering principle. Every non-empty subset of Z plus has a smallest element. Okay, let's break that apart. Z plus. Z is the integers, so Z plus is the positive integers. What does it mean that something is a subset of Z plus? It means that every element in the smaller set is also part of Z plus. Non-empty subset, so we know it has at least one element. So any one of those subsets where all of the elements in the set come from z plus, the positive integers. So 1, 2, 3, 4, 5, 6, 7, and so on. If the set is made up of only those elements, it's a subset of z plus. And it has a smallest element, which makes sense. If we're just dealing with those numbers, 1, 2, 3, 4, 5, 6, 7, whatever the set is, whatever that group is, there's always going to be some number that is the smallest. Next, we get to Theorem 0.2, which is the first form of mathematical induction. And instead of reading the definition off to you, let me just explain what we're trying to do here with induction. We're trying to prove that a certain statement is true for all positive integer values, for all positive n. Yeah, we're talking about positive integers when we do this. And so how do we prove that something is true for all values? What we're going to do is prove two things. The first thing we're going to prove is that if it is true for one number, let's call it m, if the statement is true for m, it's also true for m plus 1. Okay? Now that alone by itself doesn't tell us anything because we don't know if it's true for m. We don't know if it's true for any values at all. It might not be. But we combine that with another part, which is we prove that the statement is true for the value of 1. Okay? If we combine those two things together, we say, okay, we know it's true for 1, and we also proved that if it's true for a number, it's true for that number plus 1. So if it's true for 1, that means it's true for 2. And if it's true for 2, that means it's true for 3. And if it's true for 3, that means it's true for 4, and so on. However big we want to go, this logic extends. So that's how we can prove something using mathematical induction. If we prove that it's true for 1, and then we prove if it's true for a number, it's true for that number plus 1, then we can prove that it's true for all positive integers. The second form of mathematical induction is very similar, but the one thing that we're proving at the beginning is different. Okay? Again, we're trying to prove that a statement is true for all positive integers. And again, we prove that the statement is true for the value of 1. But now what we want to prove is that if the statement is true for all values less than a number, that it's also true for that number. And in the definition, it gets a little confusing with P of k for all k is less than m. But just understand the basic thing that it's arguing. It's saying that if we take a number m, if we can show that the statement is true for all values, all positive integers less than m, that's the part we assume. If we assume that's true and we can prove that that means it's also true for m, then we can combine those facts, just like we did in the last time, right? So since it's true for 1, that means it's also true for 2 because 1 is the only number less than 2, only positive integer less than 2. So if it's true for 1, it's true for 2. Okay, then we look at 3. Well, it's true for 1 and 2, so it must be true for 3. We look at 4. It's true for 1, 2, and 3, so it must be true for 4. So again, you can see how we start at the value 1 and then we're able to go off as large as we want. Now you might say, why are there two different forms of induction? And it has to do with the statement that we're trying to evaluate. Some statements, it's easier to prove that if it's true for m, that it's true for m plus 1. And there's others it might be easier to assume that it's true for all values less than m and then prove that it's true for m. So it just depends on what it is we're trying to prove, which of the two forms of induction we need to use. And finally, we have a definition, which is the inductive hypothesis. And the inductive hypothesis is just when we're proving that section of, so for the first form, if we look at that as an example, for every positive m, if p of m is true, then p of m plus 1 is true. When we're solving that part of the proof, we get to assume that p of m is true. That's an assumption we're making. And we're showing if p of m is true, then p of m plus 1 is also true. So that statement, p of m, that we're assuming to be true, that's called the inductive hypothesis. And again, when you're actually using it to solve something, you won't be writing it down as p of m. You'll be writing it in terms of whatever that equation might be or whatever the statement is. So the inductive hypothesis just means that thing that we're allowed to assume when we're solving the proof. The chapter ends with another theorem, 0.4, the fundamental theorem of arithmetic. But I think the only reason they include that is because it can be proven using the second form of induction. So I don't think we need to cover that here. And let me just say one final word about induction. I think when you're looking at it on paper, it makes sense pretty easily. But when you actually start trying to solve it, maybe sometimes it's a little confusing in your head because you have two statements that you have to prove are true. And if you prove both of those are true, then you get that the conclusion is true. But one of those statements, you use the inductive hypothesis, where you're assuming something is true and then proving something else is true. So just make sure you have those concepts separated in your mind, that when we're using induction, we don't get to assume that P of 1 is true. We have to prove that that's true. And likewise, we don't get to assume that for every position m, if P of m is true, then P of m plus 1 is true. But when we're solving that, we assume that P of m is true and then show that P of m plus 1 is true. So just make sure you have it sorted out in your mind, the difference between being allowed to assume something is true to then prove that something else is true, versus the bigger picture of induction, which is you have to prove that the two criteria are met. All right, so that was section 0 of Abstract Algebra, a first course. And I plan to go through the whole book this way. I can't remember exactly how much we covered in my Abstract Algebra class. Like I mentioned at the beginning, I think we went at a kind of slow pace and were very methodical about proving everything. So certain things like rings and fields, I don't even know if we covered that. We might have touched it a little bit, but I don't remember it very well. So as we go on through the book, hopefully I'll learn a lot of new things and you will too. All right, this is David Brown. If you found this helpful, please subscribe and give me a like, and come along on this journey with me about learning math. All right, thanks everyone.